Hey scholars, it's good to be back with you. Today I'd like to talk to you a little bit about matrix determinants. This may seem a little arcane at first, but it's actually pretty useful. Now, a determinant is just a function that you can apply to a matrix. A determinant is a number that tells you something about the matrix that, as I said, turns out to be fairly useful, so it's worth learning about here. So to get started, let's talk about how you write down determinant. What does that even mean? So let's say I have a matrix A, and let's make it a really simple one. That looks like a pretty simple matrix, doesn't it? Okay, so it's just a 2 by 2 matrix. So the determinant of A, and you can write this a couple of ways. You can write det of A. The more common way to see this is the two vertical bars around A. Now, this isn't my favorite notation. It makes it look like we're taking an absolute value of A. Well, we're not. This isn't exactly an absolute value. It's something else. So even though you are getting a number, it's not right to say it's the absolute value, although maybe it's related if you look deep enough. For a 2 by 2 matrix, it's pretty simple. It's A1 times B2 minus B1 times A2. So let's write that down. Now, as the matrices get bigger, this gets a lot more complicated. That's why I'm sticking with 2 by 2 right now. But chances are you're not going to calculate determinants by hand of matrices bigger than order 2 or order 3, maybe at the outside. So there's how you figure this out. Well, what would this look like if we put numbers in it? So let's try this. Let's say A is 1, 2, 3, 4. Okay, so the determinant of A is 1 times 4 minus 2 times 3. It looks like 4 minus 6 to me, and that should be minus 2. I'll get my head out of your way there. So the determinant is minus 2. Okay, well, what does that mean? Well, the thing we care most about when we're talking about determinants is whether the determinant is 0 or not. If a determinant is 0, the matrix cannot be inverted. That is, it's singular. Right? This says, right there, the determinant is non-zero, the matrix can be inverted. We care a lot less about what that actual number is, as long as it's not 0. So, where did this come from? Well, it's tough to explain in general, but let me give you a specific example for a 2 by 2 matrix, okay? All right, I'm going to start out with a system of 2 equations and 2 unknowns, and I'll call the unknowns x and y. Let's write this down. All right, and we're asked maybe to solve that system of equations. So remember what solving a system of equations means. It means finding a value of x and a value of y that make both of these true. Now, A1, A2, B1, B2, D1, D2, those are all numbers. Those are scalars. It doesn't matter what they are right now. So I'm going to go ahead and I'm going to solve for x. All right, now, I'm going to do this development here. All I'm going to ask is that you follow it. It's okay, get that out of your way. It's okay if you look at this and go, man, I never would have thought of this. Well, I'm not sure I would have either. I got this out of a book. As long as you can follow it, that's enough. You don't have to sit there and worry if you didn't think of this on your own, all right? So what I'm going to do is I'm going to multiply both sides of both equations by a number. So I'm going to multiply both sides of this by B2 and both sides of this by B1. And you'll see why here in a second. Now, when mathematicians do developments like this, it's very common for them to have a lot of false starts. It's very common for them to have some dead ends and eventually work their way through the path from the beginning of the problem to the end. What they write down in the books isn't that winding path with all the false leads and everything. When they get it done, they clean everything up to make a simple, clean, concise argument. So that's what you're seeing in these books. You're not seeing all the struggles it took to get from point A to point B. So again, as you go through this, don't worry that if you wouldn't have thought of this or it wouldn't have been this clean. Well, it probably wasn't that clean for the first person who thought of this either. So anyway, let me write this out. Okay, I think I got that right. Let me just double check here. Yep, that looks right. Now, the next step, I'm just going to subtract one of these equations from the other one. I'll kind of write that out there just so you know what I'm doing. I'm just going to subtract this equation from that one. Okay, so far so good. Now, next thing I'm going to do is notice those two are the same thing. So y just went away, and that was the whole point of multiplying by these constants up here. So let's go back up here and write this out again, and write okay, so just got it here. Well, let's go ahead and solve for x now. In fact, actually, I'm gonna erase some of this stuff here. I need more room on my board. Okay, and you can see where this is going now. I'm just going to divide by whatever's in the parenthesis. Okay. Well, dang, we've seen that before, haven't we? Well, all right. For this to work, there's only one requirement. A1B2 minus A2B1 can't be 0. It cannot be 0. If it is, you're dividing by 0. This is undefined. You can't do that. So the requirement is, so A1B2 minus A2B1 has to not equal 0, or else there's no answer, or else you're trying to divide by 0. Well, that just turns out to also be the determinant of this 2 by 2 matrix. Now, that's not a proof, that's a demonstration. This is how it works for a 2 by 2. If you were to work out the same calculation for 3 by 3, 4 by 4, it would take approximately forever, but if you did it, I think you'd get things that look like this. So this is a demonstration to show that for the matrix to be invertible, to be non-singular, this has to be the denominator here, which is the determinant, can't be 0. And when you're trying to solve a system of linear equations, it only works if the coefficient matrix is invertible, it's non-singular. So this is why we care. This is why we care about determinants. Now, how do you figure these out in MATLAB? Pretty straightforward. Let's go do that right now.